Listed below are the overhead widths in centimeters of seals measured from photographs and weights in kilogram of the seals. Find the regression equation, letting the overhead width be the predictor or x variable. Find the best predicted weight of a seal if the overhead width measured from a photograph is 1.7 centimeters using the regression equation. Can the prediction be correct? If not, what is wrong? Use a significance level of 0.05. So I will be using my TI-84 Plus to answer this question. And if you have any questions on how to go about using a graphing calculator, um, please leave a comment in the video field. Unfortunately, there's not enough time to go through all those steps in the video. But what I have here on L1, this is going to be my overhead width. And this is going to be, L2 is going to be my weight. After I plot this, I made a scatter plot of L1 and L2 with the x-intercept, the minimum x value here on the graph, please note, is 7, and it goes from up to 10 centimeters, and the weight goes on the y-axis goes from 130 to 280. So looking at the points, it looks like we have a fairly fairly strong linear relationship. And it's always important to plot your data before you determine what type of regression you're going to use, because in many cases, the relationship between two variables is not always linear. But in this case, it looks like a linear regression would be appropriate. So also I have here my two variable statistics. I have my mean of the x values, standard deviations, and the same thing for my y values. That's just here for your reference for now. What I did was on my graphing calculator, I'm also able to there's a function called linreg t-test, which is a t-test for the linear regression. And so what after plugging in the data, the null hypothesis was that the slope of the regression, the line of best fit for the regression equation, is 0, and the y-intercept is 0. If there was a 0 slope, that would imply that 0 slope would be no change in y over change in x. And that would basically imply that there is no linear relationship. So that's why the null hypothesis is that the slope is 0. And so when conducting the test, I got a t-value of 6.53, and the p-value is 0.0028. So this p-value is our lower than our level of significance of 0.05. So what that tells us is that the regression, there is a strong linear that there is somewhat of a linear relationship between overhead width and weight. The equation for the looking at the output from the calculator, we could see that the equation for the line of the best fit is going to be y equals negative 157 about. That's our y-intercept, plus 43 x. And if you look here, I just graphed the line of best fit. I plugged that into the calculator. And if you look at it, it looks like it pretty much gets as close to all the data points as possible. However, when we plug in a height of 1.7 centimeters, we're going to get a weight of negative 83 kilograms. And that doesn't quite make sense. So the problem with this equation is that the data doesn't include seals with overhead width as low as 1.7. If you look at the data points, they're all much higher. So we cannot extrapolate and assume that there's a linear relationship on all different widths, overhead widths, and that And so the regression equation should not be used to determine the weight for a seal whose overhead width is 1.7, because that's not among the sample of data we have. Interesting. If you wanted to know how we got this t-value, it's related to the correlation coefficient and coefficient of determination, which are also included in the linear regression t-test. The formula for the t-value is going to be r, which is our correlation coefficient, times the square root of n minus 2 over 1 minus r squared. R squared is called our coefficient of determination. That's that could be talked about in another video. But for now, I just wanted to show how to answer this question using a TI-84 calculator.